Hi guys, my name's Edward Mosen. So I'm going to be with you guys for better or for worse, starting Thursday through the 20th. That's the day before your exam. I would teach you for Horvath for four semesters.
You're starting this week, Thursday.
Thursday, yeah.
Yeah, through the 20th.
Through the 20th.
Is that what you said?
Yeah, I think so.
Pardon me.
Okay.
Carry on.
All right. Yeah, so you have me starting Thursday. I'm just going to be in back here catching up for the next couple of days, see where we're at, so we can kind of hit the ground running for some new material here.
Andrew has done this for me before, in the past when I took a trip to Vietnam. So I know he knows what's going on, and that's good. Because this stuff is tough. We have people trying to wrestle with this stuff, who don't know what's going on. We got disaster. He will, in the main, be doing chapters 19 and then chapter 20, and to the extent that he gets into it, chapter 21. If you wish, in support of his presentation, you could look at the lectures which I offered, which are on our website, right here. It's in the syllabus that I gave last spring. They are numbered 00022 through 00028 for chapter 19, and 00029 through 00032 for chapters 20 and 21. So you got plenty of stuff to rely on. Whatever office time arrangements Andrew wishes to make with you, I leave that up to him to determine. Now then, three types of polyprotic bronzosyloric acids. Type 1 we looked at. The parent acid is strong and molecular. Most common example, sulfuric acid molecule. First ionization extent goes 100%. So to get the hydronium ion molarity for such a solution, you have to pay attention to the second ionization and the extent to which it proceeds. That means for sulfuric acid solution, you got to consider the ionization of hydrogen sulfate ion. Based on its Ka value of 1.2 times 10 to the minus 2, we did problems. Second case, simpler case. The polyprotic parent acid is molecular, so in that respect like sulfuric acid, but in this case weak, unlike sulfuric acid. Number of examples of this kind of acid on our acid-base table. We talked in class about H2S as well as hydrated CO2, quote H2CO3, as well as true carbonic acid. Came to recognize the arithmetic for the weak polyprotic molecular acid to get the hydronium ion molarity is quite simple, because you need to pay attention only to Ka1. For all such cases, you will see that Ka2 is very small compared to Ka1, and Ka1 itself is also very small. Upshot, Ka2, practically speaking, is a no-go reaction. Consequence, no contribution to the hydronium ion concentration by Ka2. Second consequence, the molarity for the species produced when the parent acid loses two H pluses, like H2S converts to sulfide ion, or true carbonic or hydrated CO2 each convert to carbonate ion. The molarity for this anionic species is always equal to Ka2. Now, to show a proof of this above what we've already done, or in contribution to what we've done, back to hydrated CO2, 100th molar. You can't make this stuff more than about 200 molar because of the very low solubility of CO2 in water. Question, does Ka2 also contribute to the hydronium ion concentration? Answer, no. Well, that's a vote. Let's defend the vote. Number one, We defend the vote on the basis that this is a very tiny number, and it's much tinier than this number, which is also a very tiny number. These each keep with Y. The hydronium ion molarity for this solution comes only from Ka1. Well, if that's true, here's the hydronium ion calculation. Here's the chemical version of Ka1, which converts to x squared over m sub I, because m sub I less x won't change m sub I, which we see when we compute x on the basis of x squared over m sub I, x squared over m sub I, we get 6.5 times 10 to the minus 5. So let's write Ka2. Here it is. Question. What's the minimum value for the carbonate molarity if this also contributes to the hydronium ion concentration? Here's the chemistry we're looking at. For which the K value is that. Now what do we know from the sulfuric acid solution analysis? For the sulfuric acid solution, the hydronium ion molarity is m sub I plus what you get from the second ionization, which for sulfuric acid is the ionization of hydrogen sulfate ion. In that case, that ionization counts. We're saying in this case it doesn't count. But of course in this case the hydronium ion molarity does not come directly from m sub I. You have to do some arithmetic to get it. So if from the first ionization we got a hydronium ion molarity of 6.5 times 10 to the minus 6, what's the minimum value for carbonate in order for this to increase? In order for this ionization, for this reaction to contribute to this molarity? What's carbonate got to be? Because this tells you, for every mole of carbonate this reaction produces, it also produces a mole of hydronium ion, doesn't it? If this reaction produces X moles of carbonate, it produces X moles of this. And then the hydronium ion molarity for the solution would be what? It'd be 6.5 times 10 to the minus 5 added to what you get from this step, right? Sulfuric acid, that's how we found out that the hydronium ion molarity was m sub I plus sulfate ion. Here, the hydronium ion molarity is what you get from the first step plus what you get from the second step. But we're saying you don't get anything from the second step. Well, we're looking at the proof. What's the value for carbonate ion got to be at least if this is going to increase? Well, if this increases, what's the smallest increase it can show? I'm listening.
0.1 times 10 to the minus 5.
Which means this will become 6.6 times 10 to the minus 5, right? That means this got to be at least 1 times 10 to the minus 6. You agree with that?
Yes.
All right, let's put in 1 times 10 to the minus 6. Then this is going to be 6.6 times 10 to the minus 6. What kind of value we got for this? Now, because from the first ionization, from the first ionization, what did we get for the bicarb ion? Same as hydronium ion, isn't it? Right? From the first ionization, we solved it with x squared over m sub I. So from the first ionization, we got the bicarb ion to be 6.5 times 10 to the minus 5. Well, now the bicarb ion molarity got reduced, didn't it? What did it get reduced to?
6.4.
Right? Isn't this going to be what you started with? Less how much you lost because of the production of carbonate ion? Isn't that what this reaction tells you? If This ionization, if this reaction is going to contribute to hydronium ion, carbonate's got to be at least 1 times 10 to the minus 6, which means the bicarb molarity will be reduced to 6.4 times 10 to the minus 5, because it started at 6.5 times 10 to the minus 5. Would you like to look at the result of this arithmetic? Let's just look at the exponents. 10 to the minus 12 divided by 10 to the minus 5. What's that give you? 10 to the minus 7. How's 10 to the minus 7 compared to this number? It's a hell of a lot larger, isn't it? It's 10 to the 4th times larger. Which means the true carbonate molarity must compare how to 1 times 10 to the minus 6? It's got to be a whole lot smaller. And what is it? It's that. Done. We go to 1854. This is just a takeoff on the polyprotic acids which we have so far considered. Because the ones we've so far considered are diprotic. Now let's look at a triprotic. Phosphoric acid specifically. This is in the acid-base table. Ka1 for phosphoric is in the acid-base table, like Ka2 as well as Ka3. Ka1 corresponds to the ionization of the parent phosphoric acid molecule, which from a structural representation standpoint, I prefer this formula. The textbook formula will be this. But you've already heard me talk about stuff like this. Your folks are here to learn. And if I give you this formula, given that you're just learning this stuff, and I tell you to show me a picture of the most important property of phosphoric acid, which is what? Structure! You're going to make a Lewis picture where all the hydrogens are glued to phosphorus, and you will be so wrong it's terrible. That's why I tell the textbooks, and the textbook authors in particular, you can stuff those kind of formulas. They don't serve the purpose of teaching. And when they defend themselves on the basis of they know, I says, hell, if they know, what are they here for? They're here because they don't know. And you folks aren't succeeding in teaching them. So I tell these people with their fancy textbooks to get the hell out of my way. I got no use for them. Because they do not serve the purpose of teaching. You see, I have great sympathy for you folks. I'll do everything I can to help you folks learn. But I don't have any sympathy for those characters. They're making a hell of a lot of money. And what are they achieving as a consequence of making this money? Causing mass confusion and dislearning. I'm not standing for that stuff. As we have recognized, as we observe progressive Ka values for a polyprotic molecular acid, the Ka values get very small. We talked about the reason for this. You have to pull H plus from something that's minus, and that's a coulombically unfavorable process. It's hard to do. When you try to create positive-negative charge separation, that's hard to do. Okay? Now, this is, of course, for the ionization of HO of this thing. This is for the ionization of this thing. And this is for the ionization of this, leading ultimately to the production of this. You can write out the equilibrium reactions if necessary. Probably a wise thing to do, because I've told you I'm already developing exam 2, because I don't believe it's at all fair to ask Mr. Mosen to saddle this responsibility, even though I'm sure he could do a good job. Probably give you a tougher exam than me. Ooh-wee, wouldn't that be horrid? There's a question just like this on exam 2. I've already written it. It's not about phosphoric acid, but it is about a triprotic acid. Please note that for the information in the notes, we need to make a correction. The correct Ka3 value for phosphoric acid is 4.5 times 10 to minus 13, which you see in our acid-base table. But in the notes, there's a typo. It reads as 4.2 times 10 to minus 13. So the value you see in the notes corrected to 4.5 times 10 to minus 13 for Ka3. Okay? Now then, with this information before us, what do we do to get the phosphate ion molarity? Well, let's start with this. Because of the three ionization equilibria for phosphoric acid, this is the only one which involves the production of phosphate ion. So clearly, this is the equilibrium you have to consider, for which this is the K expression, if you're going to get the phosphate ion molarity calculated. So we need to get this, and we need to get this in order to compute this. How do we get this? Ka1. The value is on the board. You take Ka1 and apply to it x squared over m sub I minus x, which will reduce to x squared over m sub I. Cross multiply, take the square root, and there's your hydronium ion molarity for the 6.0 molar phosphoric acid solution. You can do the arithmetic. So we know how to get this. That comes from Ka1. How do we get this? Beside looking at the board on the right. How do we get this? You look for what K value? Isn't this the thing that's produced when the parent phosphoric acid molecule loses two H pluses? Converts to a double minus anion? And this double minus anion derived from a polyprotic acid has a molarity value that's always equal to what? Ka2! Right? There's Ka2. So we know this. This is from the first ionization. We calculate that. And before you do any arithmetic, given the magnitude of the numbers with which we are dealing, I hope you recognize, before you start doing any push-button calculator arithmetic, you're looking for a number that's damn small. Let this stuff talk to you. There's the value. 1.3 times 10 to minus 19. All right. And now we proceed to what I consider to be one of the greatest funds of Chemistry 2046. This is the calculation of hydronium ion concentration for a water solution of a hydrated metal ion Bronsted acid. Hydrated metal ion Bronsted acid, like this, or this, or any number of hydrated metal ions, some of which you see their formulas appearing in our acid-base table, a number of which you investigate by doing experiments in the 46 laboratory. Any of you approaching assignment 4? Laboratory? Well, assignment 4, you are going to investigate the chemistry of hydrated aluminum ion and hydrated magnesium ion. Their formulas are in our acid-base table and corresponding Ka values for the first ionization. As you proceed in 46 laboratory and get to assignment 6, you'll now investigate the chemistry of hydrated silver ion. You'll recognize that silver ion hydrates so weakly that you can treat hydrated silver ion as Ag plus Aq. You don't need to add the waters of hydration. But you'll also investigate the chemistry of hydrated zinc ion and hydrated copper ion, both of which have appreciable Ka values. And then for those of you who get to assignment 10, and many of you will, maybe all of you, and whatever you do that's worth credit will be considered extra credit, will be simply added to the total points you've accumulated at that stage of the game in 46L. And once you get to 900 points or more in 46L, what grade have you made? A. Yet people will come to ask me, after they've made the 900 points by laboratory work, 900 or more, they will still come and ask me, do I have to take the final? You know what my answer is? You're damn right. Now, if you take the final and make a 0, what's your grade for the course? Have you made over 900 points? What grade do you get? Huh? A. But they asked me because they don't understand the syllabus. So I say yes. Take the final. You must. After all, it is a learning experience. You should take the final. I've had a number of students in 46L who knew full well they had an A, still took the final, and those were among the students who did the very best on the final because they recognized this is a learning experience. That stands far way beyond, in terms of value, getting a grade. If you learn, you get the grade. But I know a lot of people with A's who don't know a damn thing about chemistry because they've been through a Mickey Mouse class where the A means nothing. Well, you've got to decide. And it's not easy. You're in a difficult position. Do I want to take the easy route, get the easy A, and learn nothing? But I'll have this nice transcript, nice fat GPA. Or do I want to risk the possibility of getting a lower grade while inviting the possibility of learning a heck of a lot? What do you want to do? You've got to decide. And you are in position where you're going to make that decision many, many more times because most of you are just starting your university careers. I hope you decide in favor of getting the education. On we proceed to these wonderful things. Per parent species, I can lose 3 protons. Per parent species, I can lose 3 protons. For hydrated magnesium ion, per parent species, I can lose 2 protons, showing you that these are polyprotic. All right? Now then, in order to shorthand the analysis that we wish to do for water solution of hydrated iron plus 3, I will abbreviate hydrated iron plus 3, AQ, as this. And then I will abbreviate as this. And finally, I will abbreviate this, which is what you get after this loses 2 H pluses, as this. Okay? Now we'll look at a solution, the one that's in the notes. For which the question is, what's hydronium ion molarity for this solution? How do I get it? Well, of course, as must be the case, we've got to look at the ionization equilibria which contribute to that in this solution. There's the first ionization equilibrium. And here is the second. I'm just rewriting what you already see in the notes. But I think it's necessary for us to have this stuff right before our eyes as we proceed through the analysis. Now, K equals Ka1 for quote-unquote Fe3 plus. And for the second one, K equals Ka2 for quote-unquote Fe3 plus, which is the same as Ka1 for quote-unquote Fe2 plus. Now let's look at the K values and recognize, I hope, that the K values themselves show us why this is such an interesting and challenging case. .0 times 10 to the minus 3 for Ka1, showing us that hydrated iron plus 3 is a weak acid of consequence, so to speak. There are only a couple of other weak acids which you see in our acid-base table which have larger K values than this. This is a pretty strong acid as far as weak acids are concerned. And now, the fun. The origin of the fun. Since we have just examined in fairly great detail polyprotic molecular acids.
In the book it says 5 times 10 to the negative fourth. Should we change that? Or
Oh! No, don't change that. Change what I wrote. Good, thank you. You see that I make something wrong, do something wrong, you holler. You yawp, don't be bashful. Sometimes my nose is so close to what I'm doing that it clouds my eyes. Actually, it fogs my brain. The cloud the eye is an excuse. The fog the brain is a reason. Okay? I repeat. For the molecular polyprotics, how did Ka2 compare to Ka1?
so it's much smaller.
A whole lot smaller, wasn't it? How about here?
37.
How do these values compare? Ka1 compares how to Ka2? Yes, Ka1 is larger by what factor? About? I don't want about. I want exactly. How many times bigger is Ka1 than Ka2? Come on.
10.25.
Where did you get that? Never mind. 8!
Oh, 8.
Is an 8 times 5 40? How about that? You got to do this stuff. You got to get this thing working and get this thing in the pocket and keep it there as much as possible. Now then, what is this telling us? It is telling us that if we are going to succeed in computing the hydronium ion molarity for a hydrated metal ion acid, particularly if it's fairly dilute like this solution, we likely have to consider the second ionization. That's also contributing measurably to the hydronium ion concentration. Why is it the case that there is not much difference in these K values? Why Ka2 is only a little bit smaller than Ka1, as opposed to the molecular polyprotics where Ka2 is a lot smaller than Ka1? Well, you remember for the molecular polyprotics, Ka2 involves a reaction in which you're taking H plus from something that is minus. So what are you doing here?
I guess due to the hydrated metal ion, the positive charge density is lower, so it's probably easier to strip that.
Wait a minute. You're talking about the right stuff, but not in the right way. Go ahead.
The positive charge density is actually higher. So
The positive charge density is higher. What does that mean?
it means that it's more likely to donate to H plus than
Wait a minute. For the molecular polyprotics, the second ionization involves pulling plus, specifically H plus, from an anion, doesn't it? That's hard to do because you're pulling plus from minus. Now you're pulling plus from plus. Is that coulombically favorable?
yes.
Well, tell me, Coulomb. These are each positively charged products. From a Coulomb standpoint, do they have a tendency to come together and regenerate the original acid? Or do you think from a Coulomb standpoint, they're happier staying apart? Because they're positive charged each, and like charges do what, Coulomb? They repel each other, don't they? How about that? So these are coulombically favored processes. That's why Ka2 for a hydrated metal ion acid is not much smaller than Ka1. Now let's look at it from a solving standpoint, an algebra standpoint. We've recognized we've got to pay attention to both of these ionization equilibria if we want to succeed in this hydronium ion molarity computation. Well, that means we don't know what this is. That's an unknown. We don't know what this is, because these values are, the molar concentrations for these are not the same. Okay? And we don't know what this is until we get a handle on the second ionization. Which means we don't know what this is. We got 4 unknowns. We only got 2 equations. That's a problem. You learned in algebra class, I'm sure. If you have simultaneous independent equations which involve a set of unknowns, and the set of unknowns is 4, how many simultaneous independent equations must you have involving these unknowns at the minimum to solve this? 4. We got 4 unknowns and 2 equations. Can we, at this point, solve? Now then, where do we get our other equations? The third equation comes to us from something we've already considered. What's that called? Have you been reading this like I told you? Maybe we ought to have a pre-lecture quiz. Oh, that'd be rotten. What is it?
Material balance.
Material balance. All right, let's write material balance. Material balance specifically in terms of iron in the solution, because that's the source of our hydronium ion, and that's what we're trying to get at. Mb for iron equals 0.010, which equals the molarity of this quote-unquote iron 3 plus the molarity of quote-unquote iron 2 plus, at last, the molarity of quote-unquote iron 1. Now, this tells us that if I can determine the molarities for any two forms of iron, given that the sum of the molarities for each of the three forms is the numerical label on the bottle, I can eliminate an unknown. But I'm still stuck. What do I do to eliminate this problem?
Charge balance?
Charge balance. Have you ever heard of charge balance? Consider charge balance. CB for shorthand. Charge balance is a very simple statement premised on Coulomb's law that applies to each and every stable system that contains charged particles. What does charge balance say? It says total moles of positive charge in any stable system must compare how the total moles of negative charge. Equal. You got to be equal. Well, that reminds me of a story that I think I told you already, but I'll tell you again, about a student I had in 2046 laboratory. Back in the late 60s, when I was here starting my graduate student work toward my PhD. And in so doing, assigned the task of teaching 46 laboratory. Which, of course, I am now the imperial wizard thereof. Right? The evil imperial wizard. The student had the task. Assignment 2, 46L. Do a flame test for sodium ion. And this student was quite upset because after searching the shelves in the laboratory, he could not find a bottle that only had sodium ion in it. He's looking for this bottle that just said Na+ on the label. Well, I did not know this at the time at which I saw him becoming frustrated while looking at the bottles on the shelf, not being able to find what he wanted. So I asked him, and he told me, I'm supposed to do a flame test for sodium ion, and I can't find a bottle that's just got sodium ion in it. Well, isn't that interesting? So I told him a story. I said, what kind of chemistry is this? He said, ionization reaction. I said, fine. This shows how a sodium ion is produced. A sodium atom loses an electron. I said, now keep in mind, you are looking for a bottle that has sodium ions in it only. Well, if the sodium ions only were stable, then the electrons by themselves only would also be stable. Because I could run this reaction and separate the sodium ions from the electrons. That's the only way I could get this bottle of sodium ions. Well, then I can get a bottle of electrons. So I told him, we're going to do this. You get the sodium ions, and I'm going to get all the electrons. And I'm going to open a store. Horvath's Electron Shop. I'm going to put all these electrons in bottles, taking advantage of the fact that I can now go home with a bottle of electrons. and take a big funnel and go to the socket on the wall and jam that funnel in the socket, and I open up my bottle of electrons and I pour in those electrons, and by golly, the electrons go through the wires, and the television televates, and the radio radiates, and the toaster tosterates, and I can call up GRU and say, go to hell! I do not need you anymore. And then he recognized the difficulty we're up against. You can't do this, because a collection of like-charged particles in an environment all to themselves is totally unstable. Ain't it, Coulomb? You can't do this. It ain't possible. And that provides the source of charge balance. Call it the principle of electroneutrality, because it says that any stable system containing charged particles must in total be electrically neutral. That's what it says. Well, I don't need to write all that stuff down. What we need to do is to recognize charge balance for what it is. It says total moles plus must equal total moles minus for any stable bulk, for any bulk system to be stable. So there's the whole thing. Now let's get to the value of this. Statement number 1. When we started this stuff in chapter 18, I told you that when we finished chapter 18, you would have the ability at that point to take any water solution and analyze it in detail, to whatever detail necessary, and calculate the concentrations of any species the system contains, no matter how small these molarities might be, provided these species have an existence which depends on pH. And just about every species in water solution depends on pH. And this is that last thing that we have to consider that allows us to be able to do that. So let's write charge balance for our nitrate solution. To see how it now gives us the fourth equation necessary. Here it is. 3 times the molarity of Fe3 plus twice the molarity of Fe2 plus the molarity of Fe plus the molarity of hydroniumide those are all the plus things in the pot. So we're summing up their molarities to get total positive charge. Total moles positive charge equals the molarity of hydroxide ion, because that's present in every water solution, plus the molarity of what? You haven't forgotten PSI, have you? The only other minus thing in this pot is nitrate ion. And on adding nitrate ion, to our charge balance equation, we now have the liberty of writing taking our charge balance equation, which we have just written, and setting it equal to a charge sum. How about that? What is the charge sum? In other words, for this system, what is the sum total of negative charge equal to numerically? What's the sum total of positive charge equal to numerically? It's this. Are we seeing this? You see this label? Isn't this solution 300 molar nitrate ion? Is it the case that in this solution, or any water solution for that matter, once you put nitrate ion in the system, the molarity of nitrate ion does not change as a consequence of changing pH? Is that a fair statement? The molarity of nitrate ion in a water solution does not depend on pH. Is that a fair statement? Why is that a fair statement? Come on, let's put this stuff together. What do we know about nitrate ion from an acid-base standpoint?
Stable.
Stable. Why is it stable? Come on. You looking at the acid-base table? What's conjugate acid of nitrate ion? What is it? It's nitric acid, isn't it? Isn't nitric acid categorically one of our strong acids? Well, to what extent does this nitric acid ionize in water solution? 100%. Which means its conjugate base is a weaker base than water. And if I put any such base in water solution, its molarity has no dependence at all on pH. Which tells me the charge sum for this solution is 0.030 because that is the molarity of nitrate ion in this solution. Is it fair to state also that the sum of hydroxide ion molarity added to nitrate ion molarity is this number? Why is that fair? Why?
Because we know that it's an acidic solution, then that value or the concentration of hydroxide is going to be incredibly small. So less than
How small? Number-wise?
1 times 10 to the negative 7, less.
Less than 1 times 10 to the minus 7, right? This is an acidic solution. Whatever the hydroxide ion molarity is, it's less than 1 times 10 to the minus 7. If I take any number that's less than 1 times 10 to the minus 7 and add it to this, am I going to change this? Heck no. Now then, let's take another look at this charge balance equation, because I have a strong feeling that a number of you are looking at this equation and saying, where did I get these multipliers? Or do you see where I got the multipliers? You know right away? Everybody knows? Nobody has a problem with recognizing the origin of the multipliers. I'm not going to believe that. I'm going to show you where they come from. Because I don't believe you if you tell me you all know where it comes from. I don't believe you. And I want you to know. Let's pick a simple solution. Simple because there's no acid-base chemistry of consequence in this solution other than the autoionization of water. Calcium chloride solution. Okay? Calcium ion forms a defined hydrate, but it is such a weak acid that we don't care about it. It's got a K value that's on the order of 10 to the minus 13. So, who cares about calcium ion in a solution from an acid-base standpoint? In this solution, what are the principal charged species? Boy, that's a tough question. Calcium ion and chloride ion. What are the molarities of these charged species? Come on, tell me.
1 mole.
Mole is amount. Molar. You hear that? This tells me if I want to establish an equality between the molarity of this and the molarity of this for this solution, what do I have to do to the calcium ion molarity?
Times 2.
I got to double it, don't I? Then 2 is equal to 2. And that's it. Point. When I write a charge balance equation, I take the molarity of every ion in the charge balance equation, disregard sign, I don't care if it's a plus sign or minus sign, and multiply the concentration by the charge. That's it. That's what we did there. Calcium ion is +2. We multiplied the molarity of calcium ion by 2 and set it equal to the chloride ion molarity, which is multiplied by 1, which means nothing. Okay? That's all there is to it. That's why I multiplied this by 3 and this by 2. Let's do some more practice. There's the solution. We'll keep the concentration value to 1 sig fig so we don't get lost with arithmetic. 10th molar aluminum sulfate solution. Write the principal species charge balance equation for this solution and equate it to a charge sum. I'll put the directive on the board. Write CB and equate to charge sum. There's the directive. To obey to this command of me, the imperial wizard, what did you do first? Did you write the formulas for the principal charge species in this system? All right. Let's see if you got that part right. How many wrote this? Nobody? How many wrote that? Well, got a little better that way. Okay. Remember this? When you dissolve this stuff, aluminum sulfate, to make a water solution thereof, the aluminum ions, which have a very high positive charge density, hydrate. And they form this as the well-defined hydrated metal ion. See this formula in the acid-base table. You talked about this earlier on when we were way back learning how to make system inventories and stuff like that. All right? Now then. For this solution, what is the sulfate ion molarity?
With 3 molar?
What is the aluminum ion molarity?
With 2 molar?
Now we are ready to write the charge balance equation. What do I multiply the molarity of this by? That's a charge, isn't it? And the molarity of this, pardon me, the coefficient on this?
2.
There it is. Is this correct? 3 times 0.2 is 2 times 0.3 is,
Six.
that was really tough. So the charge sum is, it's not hard. The challenge for you folks is that you haven't seen it before. But now you've seen it. And I hope you realize that, as I said, it's not hard. You got to write the formulas for all the positive ions in the pot, all the negative ions in the pot, and then write the charge balance equation. You sum up the molarities as we have shown you, multiplying each molarity by charge magnitude for the ion. And if possible, set such equal to a charge sum. Now let's be a little bit more particular. Let's pick on that solution. For this solution, I want you to take this principal species charge balance equation, okay, and write a complete species charge balance equation. Okay? We'll put that up top so you can all see. We want complete species CB equation for 0.1 molar aluminum sulfate solution. That means, based on your knowledge of chemistry, you have to write the correct formulas for all the positive ions in this thing, not just hydrate aluminum ion, and for all the negative ions, not just sulfate ion. Well, we can write what we got so far. And I'm going to write this as this. You see the parallel to what I did there? Okay? What's the next thing I write?
2 times concentration.
How about this? Next thing? Next thing? We're not done with the aluminum species.
Al plus.
You see the parallel of the chemistry this will show to our hydrated iron plus 3? Aren't they each 3 plus metal ions? All right? So we got the positive ions. Negative ions, of course, we know. Sulfate ion, what else? Anything else? Yep, there's one more.
SO4 minus, or HSO4 minus.
How about that? If sulfate ion reacts as a Bronsted base, which it does in water solution, because even though it's a very weak base, it's got a Kb value bigger than that for water. Sulfate ion will collect H plus and convert to hydrogen sulfate ion. Okay? Now then, charge sum we've recognized to be 0.6 for this solution, since it's 10th molar aluminum sulfate solution. Okay? Write on your paper now for this aluminum sulfate solution the equation for the principal Bronsted-Lowry acid-base equilibrium reaction in this solution. Principal BlAbDq. There's the directive. Well, you know how to play this game. You re-examine your inventory for principal species, don't you? And what do you select from the principal species inventory? Principal system inventory. Strongest acid, which for this solution is what? What is it? For this solution, what's the strongest acid in high concentration? Principal system inventory. This thing. Now, in order to show acid-base chemistry, I'm going to use the correct formula. And for this system, what is the principal Bronsted base? What is it?
SO42 minus.
Sulfate ion. There's the equation. What kind of extent do you think applies to this equation? Well, generally speaking, we can say large or small. What would you say?
Large.
I heard a vote for large. Any more votes for large?
Yeah, small.
No, I heard votes for small.
Yeah, small.
Somebody's wrong. Large or small? Small. Good. Hey, this is the reacting acid, but this is the product acid, and Ka for this acid bigger than Ka for this acid. Now, do you think that this reaction will proceed? Look at the Ka values. To an extent which we would have to pay attention to if we want to analyze this system thoroughly. We know the extent is small. I'm asking if you can give me a gee whiz about how small.
Smaller than water.
Smaller than water. I don't know what that means.
Smaller than... Never mind.
Those are the Ka values for the acids involved. The Ka value for the stronger acid is not quite 1,000 times that of the weaker acid.
What was the question?
The question is, does this thing proceed to an extent that we might have to pay attention to? I mean, does this thing proceed to an extent which might cause us to have to pay attention to this reaction if we want to do a thorough, accurate concentration analysis for all species? Well, let me try this question on you. If I ask you for this solution to calculate the hydrogen sulfate ion molarity, okay? Do you think for this solution the principal source of hydrogen sulfate ion is the reaction of sulfate ion with water or this reaction? For this solution is the principal source of sulfate ion the reaction we have on the board or the reaction of sulfate ion with water? I got 2 votes for sulfate ion with water. Do you think I'm going to ask you questions like this on exam too? Ha ha! You're damn right. Because if you understand the chemistry, you can do the arithmetic. And I will ask questions that will demand that you show me you understand the chemistry. Because that's where it's at. I got 2 votes that the principal source of hydrogen sulfate ion in the solution is the reaction of sulfate ion with water. I reject those votes flatly, but I accept the votes. At least I don't accept the votes, but I accept the fact that people participated. So I congratulate the participation factor. That to me beats the mute factor anytime. Why is this certainly the principal source?
Because hydrated aluminum is a stronger acid than water.
Do you think it's slightly stronger?
It's a good deal.
A great deal stronger.
How much stronger? Roughly. How much stronger acid is aluminum ion than water? Roughly. Hydrated aluminum ion.
Trillion. A lot. A lot.
I want to know the number.
10 to 14
Where'd you get that?
from the S&P.
I want to know the arithmetic you did to get that.
Yeah, 10 to 11.
What's Ka water?
1.8 times 10 to the negative 16.
Let's forget this part. How many times bigger is this than this? 10 to the 11th. That's 100 billion times stronger. So I argue, since aluminum ion is a principal species in this system, this reaction is certainly a much better source of hydrogen sulfate ion than the reaction of sulfate ion with water. Okay? We'll pick it up from this point tomorrow.